Interstellar is the year's biggest movie, partly because of the solid science behind the science fiction.
Scientists explain what really happens in Interstellar's black hole scene. Christopher Nolan spent years working with Nobel Prize-winning physicist Kip Thorne to create the most scientifically accurate black hole ever put on film. But when Cooper falls into Gargantua and ends up in that mysterious tesseract dimension, the movie throws real physics out the window and enters pure science fiction territory. Today, we're going to break down exactly what Interstellar got right about black holes, what it got completely wrong, and what would really happen if you fell into one of these cosmic monsters. The truth is far more incredible than Hollywood dared to imagine. Gargantua's visual accuracy. Let's start with what Interstellar got absolutely perfect: the visual appearance of Gargantua, the massive black hole at the center of the story. When Kip Thorne created the equations for how this black hole should look, he discovered something that surprised even him. The accretion disk, that swirling ring of superheated matter, doesn't just glow in front of the black hole. The extreme gravitational lensing actually bends light around the black hole, making parts of the disk visible above and below the event horizon. This is exactly what we see in the movie. The orange glow that appears to wrap around Gargantua isn't artistic license, it's real physics. The black hole's gravity is so strong that it literally bends space and time, creating a gravitational lens that shows us the backside of the accretion disk. To create this effect, Thorne and his team had to solve Einstein's field equations using thousands of hours of supercomputer time. They traced the path of individual photons as they spiraled around the black hole, accounting for how the extreme gravity would bend their trajectories. What's even more incredible is that Kip Thorne's visualizations were so accurate that when scientists finally captured the first real image of a black hole in 2019, using the Event Horizon Telescope, it looked remarkably similar to what we saw in Interstellar 6 years earlier. The movie even got the color right. Real black holes emit most of their light in the infrared spectrum, which would appear orange to our eyes if we could see it directly. The temperature of the accretion disk reaches millions of degrees, hot enough to strip electrons from atoms and create a plasma that glows with this characteristic orange light. Gargantua is portrayed as a supermassive black hole, roughly 100 million times more massive than our Sun. This massive size is crucial for the movie's plot, because it allows for stable orbits close to the event horizon where time dilation effects become extreme. But here's where the movie starts to bend the rules of physics. Miller's planet and time dilation. Miller's planet, the water world orbiting close to Gargantua, showcases one of Einstein's most mind-bending discoveries: gravitational time dilation. In the movie, 1 hour on Miller's planet equals 7 years on Earth. This isn't science fiction, it's real physics. When you're in a strong gravitational field, time literally runs slower compared to areas with weaker gravity. Einstein discovered this effect as part of his general theory of relativity. Time and space aren't separate entities. They're woven together into what physicists call space-time. Massive objects like black holes warp this fabric, and the warping affects how time flows. But here's what the movie doesn't tell you. For time dilation to be this extreme, Miller's planet would have to be incredibly close to Gargantua's event horizon. We're talking about orbiting just outside the point of no return, where the gravitational field is so strong that space itself is moving at nearly the speed of light. At this distance, the planet would be experiencing tidal forces so extreme that it would be torn apart within minutes. The difference in gravitational pull between the side facing the black hole and the side facing away would stretch the planet like taffy. To put this in perspective, the tidal forces near a black hole are billions of times stronger than the tidal forces the Moon exerts on Earth's oceans. Instead of gentle rises and falls in sea level, you'd have mountain-sized waves of molten rock constantly reshaping the planet's surface. Even if the planet somehow survived these tidal forces, it would be bombarded with radiation from the accretion disk. The temperature on Miller's planet would be thousands of degrees, hot enough to vaporize any water instantly. The X-rays and gamma rays streaming from the superheated plasma would sterilize the surface, making life impossible. The massive waves we see in the movie are actually a clever solution to another physics problem. Kip Thorne realized that any planet this close to a black hole would be tidally locked, meaning one side would always face the black hole. The waves represent the planet's crust being constantly deformed by tidal forces, creating a perpetual tsunami of rock and water. But the real physics problems start when Cooper falls into the black hole. The tesseract dimension breakdown. When Cooper crosses Gargantua's event horizon and finds himself in the tesseract, the movie abandons real physics entirely. But that doesn't mean the concepts it explores are impossible. The tesseract represents a 5-dimensional space where time becomes a physical dimension you can move through like walking down a hallway. In our normal 3-dimensional experience, we can move forward, backward, left, right, up and down, but we can only move forward through time. In the tesseract, Cooper can see all moments in Murph's bedroom simultaneously, as if time were laid out like pages in a book. This is actually consistent with how physicists think higher dimensions might work. String theory, one of our leading theories of quantum mechanics, suggests that our universe might actually have up to 11 dimensions. We can only perceive 3 spatial dimensions and 1 time dimension, but the others might be curled up so small that we can't detect them. If beings existed in these higher dimensions, they might indeed be able to see and manipulate our timeline the way we can see and manipulate a 2-dimensional drawing on paper. The movie suggests that these 5-dimensional beings are actually humans from the far future who have evolved beyond our current limitations. They've learned to exist in higher dimensions and are reaching back through time to save their past selves. This creates a fascinating paradox. Cooper can only send the quantum data to Murph because future humans built the tesseract. But future humans can only exist because Cooper sent the data to Murph. It's a causal loop with no clear beginning or end. But what would really happen if you fell into a black hole? What really happens past the event horizon? Here's where Interstellar gets it completely wrong. In reality, falling into a black hole would be far more violent and far less survivable than the movie suggests. As you approach the event horizon, you would experience something called spaghettification. The gravitational pull at your feet would be significantly stronger than at your head, stretching your body like a piece of spaghetti. For a black hole the size of Gargantua, this stretching would begin long before you reach the event horizon. Your body would be torn apart by tidal forces while you're still millions of kilometers away from the black hole's surface. The mathematics are terrifying. As you fall, the acceleration due to gravity increases exponentially. At first, you might experience the equivalent of a few times Earth's gravity. But within minutes, you'd be experiencing thousands, then millions of times the gravitational force you're used to. Even if you somehow survived the tidal forces, you would be bombarded by high-energy radiation from the accretion disk. This radiation would cook you from the inside out, breaking down your DNA and destroying every cell in your body. The accretion disk surrounding a supermassive black hole emits more energy than 1 billion stars. The X-rays and gamma rays would penetrate any conceivable shielding, turning your body into a cloud of ionized particles long before you reach the event horizon. But let's say you're wearing some kind of indestructible spacesuit and you make it past the event horizon. What then? According to Einstein's general relativity, you wouldn't notice anything special about crossing the event horizon. From your perspective, you would continue falling normally. The event horizon isn't a physical barrier, it's just a point in space where the escape velocity exceeds the speed of light. But from the outside universe's perspective, you would appear to freeze at the event horizon, your image getting redder and dimmer until it fades away completely. This is because time dilation becomes infinite at the event horizon. To outside observers, it would take literally forever for you to cross that boundary. This creates one of the most bizarre paradoxes in physics. From your perspective, you fall through the event horizon in a finite amount of time. But from everyone else's perspective, you never actually cross it. Both observations are equally valid according to the laws of relativity. But there's an even stranger possibility that modern physics suggests: the firewall paradox and holographic principle. Recent discoveries in quantum mechanics have revealed an even more disturbing possibility about what happens at black hole event horizons. Some physicists now believe that the event horizon isn't empty space at all, but rather a wall of high-energy particles called a firewall. This firewall would instantly vaporize anything trying to cross the event horizon. The firewall paradox emerged from attempts to reconcile Einstein's general relativity with quantum mechanics. According to quantum theory, information can never be destroyed. But black holes seem to violate this fundamental law by trapping information forever behind their event horizons. This creates a fundamental paradox in physics. Einstein's relativity says you should be able to cross the event horizon without noticing, but quantum mechanics says you should be destroyed instantly by the firewall. The resolution to this paradox might be even stranger than the tesseract in Interstellar. Some scientists believe that information about everything that falls into a black hole is encoded on the event horizon's surface, like a cosmic hard drive storing every detail of everything that's ever fallen in. This is called the holographic principle, and it suggests that our entire three-dimensional reality might actually be information stored on a two-dimensional surface. In other words, we might already be living in something like the tesseract dimension without realizing it. The holographic principle emerged from string theory and quantum gravity research. It proposes that all the information contained within a volume of space can be encoded on the boundary of that space, like how a hologram stores three-dimensional information on a two-dimensional surface. If this is true, then falling into a black hole wouldn't destroy you. It would reveal that you were already made of information all along. Your consciousness might continue to exist as patterns encoded on the event horizon, experiencing subjective time while being frozen from the outside perspective. This is remarkably similar to what happens to Cooper in the tesseract. He becomes a being of pure information, able to communicate across time and space through gravitational waves. His physical body may be destroyed, but his consciousness persists as organized information. Recent research by physicists like Leonard Susskind and Juan Maldacena suggests that black holes might actually be connected to other regions of spacetime through quantum entanglement. These connections, called Einstein-Rosen bridges or wormholes, could theoretically allow information to escape from black holes through quantum tunneling effects. This quantum connectivity might explain how Cooper is able to influence events in the past from inside the black hole. His consciousness, encoded as quantum information on the event horizon, remains entangled with the outside universe and can manipulate gravitational fields through quantum effects. So while Interstellar takes dramatic liberties with physics, it might actually be closer to the truth than we initially thought. The universe is far stranger than any Hollywood movie dares to imagine, and our understanding of black holes continues to evolve as we discover more about the quantum nature of reality. And that's what scientists really think about Interstellar's black hole scene.